Hi, let's take a look at these two sequences and let's go beyond recursive. I'm David and I'm going to try to go over something called explicit formulas. The idea of explicit formulas is I want to go down and get the nth term without knowing the previous term like we did in recursive language. I want to get the nth term except without getting the previous term. So that's my goal here. How do I get the nth term? Well, we're going to make an explicit formula. We're going to make an explicit formula. We're going to observe a pattern and try to follow it. First of all, let's observe what is the rule going on here. Is this an arithmetic or is this a geometric? Looks like the rule here is add 3 on each one. And on the g of n1, it looks like it subtracted or maybe cut in half and double check it. Yeah, we didn't subtract the same number, so we are definitely cutting in half. And that means we have a growth factor of times 1/2 or 0.5 I'm going to leave it in fraction form for this one. So this one definitely is arithmetic on the left, arithmetic. I'll just put arith for short. And this one is geometric, just kind of remind us of the basics. If I wanted to talk about this recursively, I could say a sub n takes the previous term. We now know that as a sub n minus 1. That's an object. Think of it as an object. And we just add 3 to it. That would be the recursive idea. On the right, the geometric pattern would take the previous term, Again, g of n minus 1 is an object. We're waiting for an output. We don't do any math to this except find out what the previous term is. That's how we want to look at it. And it looks like we're going to multiply this one. I'll just put a times 1/2. Oh, times 1/2. That's a nice way to think of it recursively. How do I get like the 100th term or the 30th term without building the list all the way down? So let's watch the pattern. Let me remove a little bit of this to give me some room. And let's follow this pattern here. To technically get the 5 number that we got on the arithmetic one, I took the 2 and I added 3. That gave me 5. To get the 8 number, I took the 5, which was 2 plus 3, and I added another 3. To get the output of 11 on the 3rd term, well, let me see, double check. This is starting at 0. So, yeah, technically this is the 4th step in. That becomes important. Do I start at 0 or 1? So let me get my language down. The 4th step in, where n is 3. I know it's a little weird. I had the original 2, and I added 3 times. See the pattern here? You almost see it like a triangle building out. So if I really want to get the nth term, I'm going to try to take this rule and bring it down. It looks like every single time I add a 2. So I'm going to say a of n is equal to 2. That's consistent. It's in every single answer. Now, I'm going to follow the idea of adding something here. I added 1 3. I'm going to kind of write that. 1 like this. 1 3. And then I added 2 3s. You know, you can use multiplication to add 2 3s, right? 2 3s. Think about that. And then I added 3 3s there. All right, I notice now that the n is 3 and I'm adding 3 3s. And the n is 2 and I'm adding 2 3s. Okay, I'm going to say then for the input of n, I'm going to put that I'm adding n 3s. We can write this as algebra now. Let's just kind of, use commutative rule. Remember, commutative rule means multiplication stuff can be reordered. And I'm going to make it look more familiar. 2 plus 3n. So that is how I can get any term. If I wanted the 10th term, it is technically, and I'm thinking about this now as I write it, it is the starting number 2, where n is 0, and I am adding, 10 3s. 10 3s. I could plug it in, but I'm already thinking I'm adding 30. I'm adding 30. So this looks to be 30 and 2. Looks like my answer is 32. So that's how you find an explicit arithmetic one. You follow the pattern. Just be mindful of where you start, 0 or 1. Notice here on the right, geometric, I am starting at 1. We need to be careful then. When I go to make the nth term, I'm going to double check it. I'm going to kind of play a guess and check game to see what the answer needs to be. Okay? Again, follow the pattern. How I got the 50, I'll just jump to the 50 since you're getting the idea, is I started with 200. And then I cut it in half. That's how I got the 100. Look right above. That's how I got the 100. And then to get the 50, I cut it in half a second time. The next one starts at 200, and I'm going to cut in half 3 times. Again, you can kind of see a triangle forming out there. So now let's build the connection here. This one started at 1. That's different from the other one. So watch how it's different. When n is 4, I didn't do 4 1/2 multipliers. I did 1 less than 4. 4 minus 1. So if I'm to build the explicit formula, I'm going to say let's write 200. Let's say I'm going to multiply by half in exponent notation. I'm going to multiply by half in exponent notation. So I need an exponent up here. Okay, and again, remember, when it was 4, it was technically, when n is 4, I technically had 4 minus 1, 3 of them there. And when it was 3, I had 3 minus 1. So what am I doing with the n value? It seems I'm taking away 1. Let's double check that. Let's plug and chug 1. Let's just double check it. In fact, no, let's plug and chug 2 just for fun. No, let's plug and chug 1. I got a reason why. Let's just double check it. All right, remember I said I'll do a little guess and check. Well, I'm kind of guessing n is 1. If I put a 1 minus 1, that means n is 1. Remember function notation, I plug in the value at n. This would simplify to 200 times 1/2 to the 0. Remember, anything to the 0 is a 1. So now that's 200 times 1. My output is 200. Let's check it. Step 1. What do I have for a number? 200. In mathematics, you might want to check it a couple more times, but that's the idea for building an arithmetic or a geometric explicit formula. A formula that'll tell you how to get out to the nth. Any term. You want the millionth? You now have a way of getting it. I'm David. I hope this helps.